Hi everyone, in this video we're going to talk about how do we use a heuristic approach to solve LP models. Recall that there are three different methods that can be used to solve LP models. The first one is the graphical method, and the second one is a heuristic approach. So let's look at what a heuristic is. So a heuristic is a rule of thumb for making decisions that might work well in some instances. Using the transportation problem as an example, we can use our experience and thinking logically to try to solve it manually using a table. Okay, so if you recall, this was the transportation problem that we modeled and we solved using solver. It has three supply nodes and three capacity or demand nodes. We're trying to minimize the total bushel mile when we try to ship all those supplies to those processing plants. And to make it easier, I'm going to Excel to solve this. So on this left-hand side is our slide, okay? And on the right-hand side, this was the solver model that we created and solved using solver in Excel. Now I'm going to just duplicate this cell, but we're going to solve it manually without using solver. So I'm going to delete all those values. Those formulas I put there still holds. Okay, for example, the bushel miles shipped will be the sum of those. And our total objective function is still the sum product of the distance between each pair of those groves and the processing plants. And the decision variables that we're going to decide how many bushel of citrus to ship between each pair. Okay. So we know that we're trying to minimize this total bushel mile. Okay, then thinking logically, how do we ship it? We may think, let's just start with the pair that has the least distance. For example, if we look at this table here, from Clermont to Orlando, the distance is 20. Since we're trying to minimize the bushel mile using heuristic, which is the way of logical thinking and experience, we will think about then let's just ship as many as possible on this route first because it gives us the least distance, right? And we would just go gradually to the next level of the distance that's a little bigger than this one and so on. So this one is 20 distance. So basically here, in this decision variable, we're going to ship as many as possible. However, we need to consider the constraints. For example, in Orlando, it has a capacity of 600,000. So we can't ship more than 600,000 to here, okay, between these pair. And the other one is at Clermont, the available bushels are only 300,000. So we can ship more than what we have, right? So we compare these two values. 300 is less than 600. So let's just ship out all of them. Okay, so let's ship all of them out. And with this, we shipped out all the bushel miles. So this is done. Okay, we can't do more from Clermont to other locations. That means we're going to just take the difference. So with using this, subtract this. So we know the difference there. We're going to do the same for the capacity. So the capacity, let's see. We'll just put a remaining capacity. Move this down. So we have our remaining capacity, and this is remaining supply. So when we calculate this, when we solve this problem manually, we use those calculations to help us decide what next step. So the remaining capacity would be the available capacity subtracted the received. I'm going to just copy it all the way. Okay, so now we can see that Orlando still has 300,000 capacity. But for the supply at Clermont, they are done. No more left. Okay, so now we're done with this one. We're going to move to the next one. That's the least distance. So it would be this one here, 21. And we're looking at this cell. So we're going to shift from Monadnock to Ocala. And again, we compare the two values. So there are 275,000 bushels available, but the processing capacity at Ocala is only 200. So we can only go with the smaller value. So 200,000. Then you can see the capacity here is zero now. No more shipping into Ocala. And we still, at Monadnock, we still have some remaining supply. So this one is done. We're going to move to the next least distance one. Eustis to Leesburg. Okay, so it's this value here. Then we compare the available bushels, it's 400, and the capacity is 225,000. Okay, 1,000 is the unit. So we're going to do 225. Now, zero capacity left at Leesburg, but we still have some supplies left. So this value is used. Then we go to the next. So 25, right? The next least distance pair is between Clermont and Leesburg. So we're going to look at this value here. So for this value, we see we no longer have any supply available. So we basically can't really ship more here. So I'm just going to give it a 0 because we no longer have supply and we no longer have any capacity left. Then we move to the next least distance one, 25. That would be 30, right? 30 will be this value here. So this value, we can see that we still have 300,000 capacity left, but the supply is only 175,000. So we'll go with the smaller value. Okay, so this is done. We still have some capacity there. This value is used. We just cross it out. Then we go to 35, which is that next least. But we can see that the supply at Eustis is already gone. So we shipped all of them out already. So we are not going to do anything here, just a 0. And then move to the next one. So 40. 40 is next least distance. So we still have some supply left at Monadnock. But if we look at the capacity, it's already 0. So we can really ship more to Leesburg. Okay, so this is not used. And then 40, then we move to 50. So this value here. We have some supplies left and also capacity. And comparing the supply and the capacity, we have less supplies. So we'll go with smaller value, 75,000. And then we have some capacity left here. We'll cross this value. And then the last one would be this value here, the 55, this one. Okay, so at Clermont, we don't have any supply left, right? And even though Orlando has some capacity left, that's okay. Because when we look at this problem earlier, we modeled this problem. Remember, we look at the total supply and the total capacity relationship, and we found that we have more capacity than the supply. So in this problem, we're going to ship out all the supplies, but not using up all the capacities. So now if we look at this result, okay, and comparing to the result that we got by using solver to solve it. So on this slide, this is the result, okay. Let me enlarge this. When we use solver to solve it, the total distance measured in bushel miles is 24 million. Here we have 150,000 more than this optimal solution. We followed the logical thinking of shipping the most to the least distance and move to the next least distance, shipping the most as possible, and continue. So logically it's correct. However, the result we got is not optimal. So there must be a step that we missed. And I encourage you to take a look and see if you can find out which step we missed and how do we get this optimal solution when you solve it manually. But the point is that a heuristic is a rule of thumb of making decisions that might work well in some instances, but it does not guarantee optimal solution. Okay, it may work well in some instances, and in some very complex models, like in nonlinear situations, a heuristic is used a lot to help solve problems. But in those simple LP models, we don't really need to use it. We use the more rigorous algorithm. It's called the LP simplex. Or if we only have 2 decision variables, then we can use the graphic method we talked about earlier to solve them. A heuristic works some situations. Just remember that it does not guarantee an optimal solution. Okay, so in one of the problems that we talked about before, Chapter 3, the homework problem, the TV ads and the newspaper ads problem, we didn't solve this problem manually, right? Remember, we look at the customer per dollar ratio, and then we started from the one that has the highest ratio. We feel that so since the first group of newspaper ads would reach the most customers per dollar spent, we said let's just fill this group first. So we give a 10 to this group, and then we calculate how much money is left, and then we went to the next highest customer ratio group, which is the TV ads, the first 1 through 5, and we filled a 5 here. Then we went back to this second group in the newspaper ads because it has the next highest customer per dollar ratio, and so on. So we solved this problem using heuristic approach, and it is the optimal solution. Okay, so in this way, in this specific problem, we find the way. And remember, the reason we did this heuristic is to look at how this problem will be solved so that we can simplify the constraints. So some of the constraints really do not need to be written out, because when the problem solves, those constraints will be satisfied automatically. So that's a good use of heuristic in formulating LP models. When you look at the model and when you expect there are some constraints that can be fulfilled automatically, so now we can see that those constraints will be like redundant constraints. Okay, so they can be fulfilled automatically, then you don't really need to write them out, especially if it takes some effort to convert, for example, in this problem, the logical statement, the if-then-else statement into math constraints. We can just leave them. So this is the approach called the heuristic approach, and it is very helpful in helping us simplifying the LP models. And it's also a rule of thumb for helping in certain situations when the model gets complex and when there's no way to find the optimal. And so heuristic is used in solving nonlinear programming models. But remember, it does not guarantee an optimal solution.